Hello everyone, my name is Hossam Abdelrahman. I'm an undergraduate research assistant in the Food Science Department supervised by Dr. Maria Corradini. The title of my research project is From Food Microstructure to Stability. The research focuses on understanding the shelf life of microstructure food matrices by looking at structural changes and deterioration, utilizing our lovely 3D printer, which is the BioX printer. My main responsibilities in this project include literature review, choosing suitable software which is going to be compatible with our BioX printer in order to design 3D models, and exploring various slicing tools in order to further modify the 3D models and make sure that it is prepared and free from errors before printing. And most importantly, I was working on optimizing the 3D prints by trying and changing the printing features in order to get the most consistent optimized structure possible. One of the most important concepts covered in this research is the key term 4D printing. 4D printing is very similar to 3D printing. Both have printing in all three dimensions, except that in 4D printing another dimension is being added, which is time. The concept of 4D printing is really important in this research project, as we're trying to understand the structural changes and deterioration over time after we print those 3D food matrices. In order to create those 3D models, a CAD software program is needed. CAD stands for Computer Aided Design. There are many CAD softwares available in the world. And in the project, we had to navigate through various software programs and choose one that is going to be suitable for the research and at the same time compatible with the BioX 3D printer. After intensive research and literature review, Blender and Fusion 360 were the best options to go for designing and slicing our models. When it comes to printing, a specific food grade ink was used for this research project. This grade ink was Zane-based. Zane is a corn protein that is very hydrophobic. The grade ink is composed of 2:4 Zane to solvent in a weight-by-weight ratio. The solvent was composed of 3.8 grams of 2-propanol and 1.2 grams of water. The solution has a unique property called viscoelasticity. The viscous part, which gives it the liquid property, allowing us to extrude Zane through the nozzle, and the elastic part, which gives it the solid property in order to stay in place once it sits on the print bed. Here is an example of food matrix. This food matrix was printed under a pressure of 10 kilopascals, and the print head speed was 5 millimeters per second, and for a total of 7 layers. One of the cool things is that in the lab we get to examine and study those food matrices under the microscope in order to measure the distances between vertices or even angles. After intensive research, it turns out that our Zane works best at a pressure of 50 kilopascals in order to extrude enough amount of Zane, and having a print head speed of 10 millimeters per second, which is fast enough to have the right definition of the shape, and having a print bed temperature of 10 degrees Celsius in order to reduce the viscosity of Zane once it sits on the print bed, allowing it to solidify quickly, and having a time gap of 1 minute between layer depositions, which also helps in the solidifying of Zane. Some future work and implications: printing and designing models that resemble realistic food products, and incorporation of fats and oil droplets into the matrix, analyzing physical and chemical characteristics and studying the shelf life of the food matrices by looking at structural changes and examining deterioration. Here's just a special thank you to Luigi, our PhD candidate in the lab, and Dr. Maria Corradini, my supervisor, for being guidance to me throughout the summer. And thank you everyone for watching this, and have a great day.